next topic of the chapter, Fermat's theorem. So, what is the statement of the Fermat's theorem? Let P denote a prime, that is, P is a prime number, and A belongs to Z means A is integer, such that the greatest common divisor of A and P is 1. And what is its meaning? This meaning is given here that P does not divide to A. The greatest common divisor of A and P is 1 means P is not divisor of A. Because if P is divisor of A, then P becomes greatest common divisor of A and B. Because greatest common divisor means the common divisor. So P is a divisor of P itself. And if P is divisor of A, then P becomes a greatest common divisor. But here, the greatest common divisor of A and P is 1 means P is not the divisor of A. So it means this meaning of these both are same, that greatest common divisor of A and P is 1, or P is not divisor of A. Then A raised to P minus 1 is congruent to 1 module P. That is where to show this. A raised to P minus 1 is congruent to 1 module P. And for every integer A raised to P is congruent to P module P. Okay. So where to show this? So proof of this theorem. The question is on this theorem is what? State and prove Fermat's theorem. So proof of this theorem. Let us consider P minus 1 integers. What are that? A, 2A, 3A, P minus 1A. So these are the P minus 1 integers in number P minus 1. These are in a number P minus 1. And if note that if IA and JA be any two members of this set, then assume that IA is congruent to JA module P. Then what happens? Where obviously I and J runs from 1 to P minus 1, and I is not equal to J, suppose. If we consider any two members of this set, then what happens? If suppose that these two are out of these two are congruent, and then we have I is congruent to J module P means P divides to IA minus JA, and that is P divides to I minus JA. Take this A as common. Then P divides to I minus J because P does not divides to A, as greatest common divisor of A and P is 1. And by using Euler's theorem, Euler's lemma, that if P is prime and P divides to A into P, then P divides to either A or B, one of them. But P does not divides to A means P divides to I minus J. But this I and J both are less than or equal to P minus 1 means their subtraction is also less than strictly less than P, or is less than or equal to P minus 1. And P divides to this number means this number is 0, because I minus J is less than P, and P divides to I minus J means I minus J is 0. Because larger number divides to smaller number, then that smaller number must be 0. And then we have I is equal to J, which is contradiction to the fact that I is not equal to J. So that is any two distinct members are not congruent module P of this set of these integers. Out of these P minus 1 integers, no two are congruent module P. This proves that is IA is not congruent to JA module P for all I runs from I and J runs from 1 to P minus 1. There is no member, any two member of these set, these elements, these integers are congruent to each other module P. So we have this. So no two members of set A, 2A, 3A, P minus 1A are congruent module P. No two distinct members out of this are congruent module P. And therefore all members of A, 2A, 3A, P minus 1A, this set belongs to distinct residue class module P. Because when two different belongs to the same residue class, if they are congruent to each other, the elements are not congruent to each other, integers are not congruent to each other, they belongs to the different or distinct residue class module P. As when these elements belongs to the, if they are related to each other, as if X is related to Y, then X belongs to Y bar. So no two are congruent to each other, and so no two out of these members belongs to the same residue class, that is all the members belongs to the distinct residue class module N, module P. Okay, but we know that there are precisely P residue classes module P. But we know that under module P there are P distinct residue classes. What are that? 0 bar, 1 bar, 2 bar, 3 bar up to P minus 1 bar. 1 bar. Okay. So there are precisely P residue classes module P, namely this. And so no member, no any two member of these sets belongs to the same residue class. That is, all these belongs to the different class. Means suppose A belongs to suppose 1 bar, then 2A does not, or any member out of remaining belongs to the 1 bar. So A belongs to 1 bar, then no member other than A belongs to 1 bar. Then 2A, suppose 2A belongs to 4 bar, then no member other than 2A belongs to the 4 bar. That is, no one out of these members belongs to the 0 bar. Out of these, first note that no member of these P integers belongs to the 0 bar, because if we assume, suppose one of them, suppose IA belongs to 0 bar, then what do we have? Where I is also same, value of I is runs from 1 to P minus 1. Out of these, 1 from I is what? Out of these 1 to P minus 1. Value of I is what? Either 1 or 2 or 3 or P minus 1. Okay. Then what happened? We assume, if we assume IA belongs to 0 bar, then IA is congruent to 0 module P, because of this. The element belongs to 0 bar, IA belongs to 0 bar, means IA is related to 0. IA is congruent to 0 module P. And implies by using definition of congruence relation, A is congruent to B module P, A is congruent to B module N, if and only N divides to A minus B. That is, P divides to IA minus 0. That is, P divides to IA, implies P does not divides to A. And so P divides to I. That's P does not divides to N by Euler's theorem or Euler's lemma. And this is not true, as I is strictly less than P. I is strictly less than P. So P does not divides to I, or either I is 0. So, but I is not 0. I runs from 1 to P minus 1. And so this is contradiction. This is not true. And therefore, this IA does not belongs to 0 bar. That is, no one out of the set A, 2A, 3A, P minus 1A belongs to 0 bar. Means all these belongs to either 1 bar, 2 bar, 3 bar, up to P minus 1 bar. That is, hence A, 2A, 3A, P minus 1 belongs to the distinct residue class module P, namely here remove this 0 bar, belongs to what? All distinct residue class belongs to the 1 bar, 2 bar, 3 bar, P minus 1 bar in some order. Here delete this 0 bar here from this. So because no one belongs to the 0 bar, and all these members A, 2A, 3A, P minus 1 belongs to the distinct residue class. So what we have, that this means A, 2A, 3A, P minus 1A are congruent module P to 1, 2, 3, P minus 1 in some order. Because when suppose 2A belongs to 3 bar, then 2A is related to 3. Okay. So suppose 3A belongs to 5 bar, then 3A related to 5. And no one belongs to the same residue class, means all these members are what? Congruent to 1, 2, 3, P minus 1 in some order. And therefore, we have, by using this theorem, we have what we have? A into 2A into 3A, P minus 1, A is congruent to 1 into 2 into 3 into P minus 1 module P. By using theorem that if A is congruent to B module N and C is congruent to D module N, then AC is congruent to BD module N. AC is congruent to BD module. And that is what is the meaning of this statement? That is, A is congruent to one of these, 2A congruent to one of these, P minus 1 minus A is congruent to one of these, and therefore this multiplication of this is congruent to multiplication of this module P. That is A into 2A into 3A into P minus 1A. The multiplication of this is congruent to 1 into 2 into 3 into P minus 1 module P. And take A as common. The multiplication of A into A P minus 1 times, that is A raised to P minus 1. That is, if we multiply A 3 times, then we have A raised to 3. If we multiply A by 4 times, then we have A raised to 4. Like that, A into A into A into A P minus 1 times. Therefore, we have A raised to P minus 1 into, in bracket, 1 into 2 into 3 into P minus 1. And this is 1 into 2 into 3 into P minus 1 module P. That is, this is P minus 1 factorial. This is P minus 1 factorial. And this P minus 1 factorial and greatest common divisor of P minus 1 factorial and P is 1. Therefore, cancel this P minus 1 factorial. We have A raised to P minus 1 is congruent to 1 module P. And then multiply by both sides by A. This is the actually Fermat's theorem. Multiply by A. We have A raised to P minus 1 into A raised to 1. That is A raised to P. Here write A. Correction is here. Write A module P. Don't write AP. Also here is the correction. Write here A. Therefore A raised to P is congruent to A module P. So this is the Fermat's theorem. So question on the Fermat's theorem is what? State and prove Fermat's theorem. So the question examples on the Fermat's theorem. The first example is find remainder of Z raised 7 raised to 486 when divided by 30. So that 13 is prime number. P is denoted by P. 13 is prime number. And take A as integer 7, the 7. And is not multiple of P. That is 13 does not divide to 7, obviously, because 7 is smaller than 13. 13 does not divide to 7. And then by Fermat's theorem, what do we have? That if what is the Fermat's theorem? That is, if P does not divide to A, then A raised to P minus 1. That is 13 does not divide to 7, therefore 7 raised to 13 minus 1, that is 12, is congruent to 1, module P, module 13. Okay, so by Fermat's theorem, 7 raised to 13 minus 1 is congruent to 1 module 13. That is 7 raised to 12 is congruent to 1 module 13. And 7, the power of 7 is 486. So multiply this 12 by such a number that we have the number nearest to 486. And that power is 40. That is taking 40 power of both sides. So 7 raised to 12 raised to 40 is 1 raised to 40 is congruent to 13. And then 7 raised to 12 into 40. That is A raised to M raised to N is what? A raised to M into N. So 7 raised to 480 is congruent to 1 module 13. And then we now find 7 square. What is 7 square? Is 49. Is congruent to what module 13? That is, if we subtract 10 from this 49, then we have the answer 39, and 13 divides to 39. Okay, that is 13 3s are 39. So fill this blank place. That is, it is 10. Then 7 square is congruent to 10 module 13. Then 7 cube, that is multiply both sides by 7. That is 7 square into 7 is 7 cube, and 10 into 7 is 70 module 13. And 17, divide 17 by 13. That is, we have the remainder 5. If we divide 17 by 13, then 5 is the remainder. So 17 is congruent to that number module. 70 is congruent to 5 module 13. So A is related to B and B is related to C. Therefore, A is related to C. So right here that 70 is congruent to 5 module 30, because 70 minus 5 is divisible by 13. Okay. So the 7 raised to 3 is congruent to 70 module 30, and 70 is congruent to 5 module 13. Therefore, 7 raised to 3 is congruent to 5 module 13, because this congruence relation is a transitive relation. And then multiply, that is 7 raised to 3 into 7 raised to 3 is congruent to 5 into 5 module 13. And then 7 raised to 6 is congruent to 5 into 5, 25. But if we divide 13 by 25, then the remainder is 12. That is 13 ones are 13 plus 12 is 25. So we have here 12. And then what is the multiplication of these two, 1 and 2? That is 7 raised to 480 into 7 raised to 6 is 1 into 12 module 13, because we know that A is congruent to B module N and C is congruent to D module N. Then A into C is congruent to B into D module N by using that theorem. And so we have 7 raised to 486. This is 7 raised to 486. Base same, therefore addition of powers. 1 into 12 is 12, module 13. And if you divide 12 by 13, then 0 is the quotient and 12 is the remainder. So if we suppose if you have here if you have here 17 number, at this place we have 17, then if we divide 17 by 13, then 1 is the quotient and 1 is the quotient and 17. Suppose 13 plus 4 is the remainder, so remainder is 4 right here, answer remainder 4. So divide this number by 13, we have the remainder 12, and therefore the remainder when the final answer is what? The remainder when this 7 raised to 486 is divided by 13 is 12. So this is the answer. This is the same type question. We'll see first this question and then find the remainder when 8 raised to 401 is divided by 13. Here is the 7 raised to 486 is divided by 13. Here is what? 8 raised to 408 is divided by 13. So 13 does not divide to 8, and therefore by Fermat theorem 8 raised to 13 minus 1, that is 12, is congruent to 1 module 13. And then we take the power of this 8 raised to 12 such that we have the number nearest to 401, and that is 33. 8 raised to 12 raised to 33 is 396, is nearest to 401 and is congruent to 1 module 13. Take the 33 power of both sides. And then starting with 8 square. 8 square is 64. 64 is congruent to what module 13? That is, if we do subtract 12 from this, we have the answer. What we have the answer? 52. And the 13 divides to 52. That is 13 divides to 64. And then take square of both sides. 8 square is 8 raised to 4 and 12 square is 144. And if you divide 144 by 13, then 1 is the remainder. So 8 raised to 4 is congruent to 1 module. And then take multiply by both sides by 8. 8 raised to 5. 8 raised to 4 into 8 is 8 raised to 5. 1 into 8 is 8. And then 1 into 2, that is from 1 and 2, what we have? 8 raised to 396 into 8 raised to 5 is congruent to 1 into 8, that is 8. And if we divide 8 by 13, then 8 is the remainder. Okay, and therefore the final answer is what? If you divide 8 raised to 401 by 13, then 8 is the remainder. So if we divide 8 by 13 like this, all right, 8 is equal to 13 into 0 plus 8. So 8 is the remainder when 8 raised to 401 is divided by 13. So similar these problems on the Fermat theorem. So we'll see the remaining problems. What is the remaining problem? These are find the remainder when 7 raised to 361 and 7 raised to 362 is divided by 11. So tackle this first 7 raised to 361. So 7 this 11 does not divide to 7, right? First 11 does not divide to 7, and therefore by using Fermat theorem, that 7 raised to 11 minus 1, that is 7 raised to 10 is congruent to 1 module 11. Then taking 36 power of both sides, 7 raised to 10 raised to 36 is congruent to 1 raised to 36 module 11. That is, take the power of 7 raised to 10 in such a way that we have the answer nearest to 361, and that is 360. And then 7 is congruent to 7 module 11, because 11 divides to 7 minus 7, that is 11 divides to 0. Then 7 square is congruent to 7 square is 49. It's congruent to 5 module 11, because 11 divides to 49 minus 5. And then multiplying 1 and 4, that is multiplication of corresponding side of 1 and 4, 1 and this 3, not 4. Then what do we have? 1 and 2, 1 and 2, right here, 2, 1 and 2. We get 7 raised to 360 into 7 raised to 1 is 7 raised to 361. 1 into 7, congruent module 11. Okay. And multiplying this 1 and 3, we have 7 raised to 360 into 7 square is 7 raised to 363 with this number. Actually, this is 362 right here, 362, because 7 raised to 360 into 7 square is 7 raised to 363 is congruent to 1 into 5, that is 5 module 11. And then add this, that is, if we know that the theorem a plus a is congruent to b module n and b is congruent to c module n, then a plus b is congruent to c plus d module n. So we have this by using this theorem. And then this 7 plus 5 is 12, and if we divide 12 by 11, then 1 is the remainder. 1 is the remainder, and so remainder is 1. That is, if we divide this number by 11, then 1 is the remainder. So same question here. What is the remainder if 12 raised to 12 is divided by 13? So by using Fermat theorem, we have 13 does not divide to 12, and therefore 12 raised to, and 13 is prime number, and 12 raised to 13 minus 1, that is 12, is congruent to 1 module p. 1 module p. By using Fermat theorem, 12 raised to 13 minus 1 is congruent to 1 module p, because 13 does not divide. And 12 raised to 13 minus 1 is 12 raised to 12. And therefore 12, if we divide, 1 is the remainder when 12 raised to 12 is divided by 13. 12 raised to 12 is divided by 13, then 1 is the remainder. This is the answer, 1 is the remainder. So show that 7 raised to 10 minus 5 raised to 10 is divisible by 11. That is the remainder is 0. That is, show that this number is divisible by 11 means remainder is 0, like this. Here is the remainder is 1, like that. So 11 does not divide to 7, and therefore, and 11 does not divide to 5. So Fermat theorem 7 raised to, for this 7 raised to 11 minus 1 is congruent to 1 module, and for this 5 raised to 11 minus 1 is congruent to 1 module, and that is 7 raised to 10 is congruent to 1 module 11, and here is 5 raised to 10 is congruent to 1 module 11. And then taking the subtraction, that is a minus c. If a is congruent to b module n and b is congruent to a is congruent to b module n and c is congruent to d module n, then a minus b is congruent to this 1 minus 1, that is c minus d, that is 0 module 11, and therefore 0 is the remainder if this number is divisible by 11. Find the unit digit of 3 raised to 100 by using Fermat theorem. We have to find the value of 3 raised to 100, but it's unit digit. That is the last digit of this 3 raised to expansion of, if we obtain 3 raised to 100, and what is its last digit of that number, unit digit of that number. So 3 is congruent to 1 module 2 we have. So we start with 3 is congruent to 1 module 2 because 2 divides to 3 minus 1. Then we have 3 raised to 100 taking 100 power of this. So we have this, and then 2 divides to 3 raised to 100 minus 1. 2 divides to 3 raised to 100 minus 1. And 5 does not divide to 3. Therefore by Fermat theorem, 3 raised to 5 minus 1, that is 3 raised to 4 is congruent to 1 module 5. Taking 25 power of both sides, then we have 3 raised to 100 is congruent to 1 module 5, and that is 5 divides to 3 raised to 100 minus 1, and the greatest common divisor of 2 and 5 is 1. Hence 2 into 5 divides to 3 raised to 2 into 5 divides to 3 raised to 100 minus 1. Hence 10 divides to this number, and thus 3 raised to 100 is congruent to 1 module 10, and hence 1 is the remainder when 3 raised to 100 is divided by 10, and that is unit digit of 3 raised to 100 is 1. If 7 does not divide to a, then prove that a raised to 3 plus 1 and a raised to 3 minus 1 is divisible by 7. So 7 does not divide to a by Fermat theorem. A raised to 7 minus 1 means a raised to 6 is congruent to 1 module p, module 7, and that is 7 divides to a raised to 6 minus 1. But a raised to 6 minus 1 factorization is a cube minus 1, a cube plus 1, and then 7 divides to this a cube minus 1 plus into a cube plus 1, 7 is prime, then by Euclid's lemma, 7 divides to one of them. That is 7 divides to a cube minus 1 or 7 divides to a cube plus 1. That is the answer of the, that is prove that this 7 is divisible by 7 means 7 divides to either this or this. So we have this. So these are some problems on the Fermat theorem. Their answers are given. So solve all these problems. So we will see the next topic in the next lecture.